So we're going to talk about adding, subtracting, and one of the three types of multiplication of vectors. And the adding and subtracting is really straightforward, really basic, but it does help us like conceptualize what vectors are and how they behave with each other and that sort of thing. Like some of these fundamental ideas. In fact, an interesting idea in mathematics, you learned some of the fundamental axioms of our standard mathematical system, back in grade 1, you started learning them. And you've been building on that all throughout your mathematical career so far. And even things like bed mass. Why is bed mass the way that it is? Does it have to be that way? No. It is what we call contingent. That's a nice word. And part of the reason why we do it, there are reasons why we do these things. It's convenient, it's nice, the rules are very consistent. Sometimes that's the reason. But it's also just we need to have a common language, right? So we need to make sure that we all know that multiplication happens before addition. Otherwise, we'd be representing ideas in different ways. So part of it is a common language, but it's interesting. And if you were to study math, and I know some of you are not going to study math. I know many of you won't. And so you kind of think, that doesn't apply to me. But it does, because it's interesting to think about how the rules of mathematics are made in a certain way. Were they made in a different way? How would that change things? And there's a whole area of mathematics, often called pure math, that talks about that sort of thing, that analyzes what we call the axioms, which are the formal fundamental rules of a particular mathematical system, and then how you build on those over time. And in fact, there was somebody, a great mathematician by the name of Gödel, who has a theorem called Gödel's incompleteness theorem that it's kind of hard to explain, but it's really interesting. It talks about how no mathematical system can be complete in that all truths are provable and representable, and so it has some real drastic impacts on math and all kinds of things. Anyway, so there's like a lot to it, right? And that stuff's pretty deep stuff. But my point about this little sidetrack here is we are building those fundamental axioms in terms of vectors right now. What does vector multiplication mean? What are the rules? What are the rules of addition? What are the rules of subtraction? Because they could be designed in different ways. And because numbers, if you think of a number as a vector, it has a magnitude 5 and a direction to the negative 5. It's just a one-dimensional kind of thing, or where you can only go left and right? One-dimensional, where 2 dimensions would be x, y plane. So you could think of it that way, but these kinds of vectors, because they are in 2 dimensions and we're going to explore 3 dimensions, becomes a lot more difficult. The adding and subtracting is not as trivial, and the multiplying certainly is different. And I told you there's at least that we're going to explore 3 different types of vector multiplication. But the one we do today is pretty straightforward, and it's kind of intuitive. But it still, to me, is interesting that we are building, like we're coming up with the building blocks of vectors mathematically, and so it's pretty crucial. Anyway, let's dive into it. Adding vectors that have the same direction. So the resultant vector will be in the same direction as the 2 original ones, and the magnitude will just be the sum of the magnitudes. Oh my gosh, this is what you would expect. So I'm going to draw a couple of vectors here, and I'm going to pretend that they're perfectly horizontal, even if they don't end up looking that way. There's vector A and vector B. It will look like this. And then I'm going to, I wonder if I can copy and paste these things. Can I do that? Copy. Oh no, it's going to paste it over there, isn't it? Yeah, forget it. I'll just redraw it and try to draw it the same length. So the resultant vector will be A. Oh, geez, that was terrible. A, good enough. And B, good enough. And then if this is R, right, so I've got the R vector is equal to the A vector plus the B vector. Probably what you would have guessed. And most of you have taken physics, you've already done this sort of thing. When have we seen this already in high school maths? There is a time. I remember the quadratic functions unit in grade 10. Well, there's 3 of them, but the one where you do all the word problems and the one where you're going with the wind and against the wind. Do you remember those? Remember those kinds of questions, at least vaguely? Not really. Some of you do, some of you don't. So that's like you've got 2 vectors and you're adding the speed of the wind to the speed of the plane, and that's the overall speed, right? So very similar. So what about if we're adding vectors that are parallel but opposite? So it's important that they're parallel, because if they have different angles, if they're not parallel, then the way we add is very different. But if they happen to be in the same direction or opposite directions, then the vector addition is very simple. It's like adding and subtracting negative numbers, right? So again, this is going to be very intuitive to us. If I have vector u going this direction, and I'm going to try to draw a vector v to be the same magnitude, but opposite, so the magnitudes are equal but opposite, then the resultant vector u vector plus v vector is the 0 vector. And we don't call it 0, we call it the 0 vector. That's different from 0. Remember I said this yesterday. When it's important that some of these processes, adding, subtracting, multiplying, the output we get, the result we get is a vector, and sometimes the result we get is a scalar, or just a number, a magnitude. And when we add, it's a vector, so it's the 0 vector. It's not equal to 0. That would be like a scalar, but there's no reason why it turns it into a scalar. It's just a 0 vector, which has no direction and no magnitude. If the magnitudes are not equal, then the direction, this is like a complicated way of saying, duh, this is what you think it is. If the magnitudes are not equal, the direction is the direction of the largest vector, and the magnitude is the absolute value of a minus b. So the reason why I put the absolute value around it is it means regardless of which one's bigger. So if b is bigger, when I do a minus b, I get a negative, but magnitudes are always are always positive, I meant to say. So the absolute value idea, or the magnitude of this, is always going to be positive, whether you see this as magnitude or whether you see this as absolute value, same idea. It'll be a positive, right? Because magnitudes are always positive. So if I have a vector going this way, actually I'll make this the b vector, I'll make this the bigger one, and the a vector going that way, then the resultant vector is going to be whatever's left and going the direction of the bigger one, because it's going to be like positive 6 minus 4. So you get positive 2, right? Like it's, or plus negative 4. So this is going to be R. Okay? Easy enough? All right. What about non-parallel vectors? So we have this thing, and this is important to remember. We add them by placing the vectors tip to tail. So I'm going to redraw these vectors again as best as I can to be similar. So there's vector A, but I'm going to move vector B so that its tail starts at the tip of A, and then the resultant vector of A plus B is from the tail of A to the tip of B. And you could add 3 vectors, 4 vectors, all of them by just in a chain lining them up. Okay. Yes.
How come the R vector is starting from the A to from the end of the A instead of it wasn't going the other direction?
Because that's the direction of the vectors. It should start where the vectors start and go the same direction as the vectors are going, right? Good question. Let's visualize this. If I start at my house and I walk this direction and then I get to that point and then I walk that direction, where am I going to end up? Well, that's what vector addition is. I can think about 2 different types of traveling. Walking 3 kilometers south plus walking 1 kilometer west. If I just talk about those as directions, that's one thing. If I actually do them, I walk the first part, I get to a position, and then I turn and I walk the second part. Like I'm adding those 2 walks together. I could do those 2 walks individually, but if I add them together, that's literally what vector addition is. Does that make sense? So you would always absolutely start at whichever one you begin with. Now, here's something that you can think about and visualize and try yourself on paper. What if I did B plus A? What would that look like? And think about this. If you walked 3 kilometers south, then 1 kilometer west, is that the same as walking 1 kilometer west, then 3 kilometers south? It's a little bit harder with vectors because you got to draw them the right way. And if I was doing it, I wouldn't just draw right angle vectors. I would try to do some like this. But it would be interesting to try that. And that is those properties, again, those are part of the fundamental properties of a mathematical system. Are the operations associative, distributive, commutative? These are things that we will talk about when it gets more interesting, I think today when we do some multiplication. But anyway. Okay, subtracting vectors. Treat A minus B as A plus negative B. That seems strange. Like, yeah, why wouldn't I treat it that way? It means the same thing. But what does negative B mean? It means I take the B vector and I draw it the other direction, right? So this is negative B. So A minus B is going to be A, try to draw that A again properly, plus the negative of B, which goes like this. So that definitely gives me a very different resultant vector. That's A minus B because I added negative B to A. That seems trivial, but I don't know. There's something about that to me is like, okay, we're working with vectors here because I can't just subtract a vector. Because what does that mean? But I know what a negative vector is, and I know how to add vectors. Right? So I can do this. All right, from the diagram below, find a single vector that is equivalent to each of the following. Oh, some of this stuff seems so simple, but there's still some big thinking going on in here. I guess you need a minute to draw that all out, so I'll give you a minute. I don't know that your drawings need to be perfect for this, folks. You can kind of just sketch it because you can label it, and you're going to get the idea from going through it. This is not something that you're going to have to worry too much about looking back at carefully. I don't think. All right, we got that. Anybody have an answer to this first question? Or are we still drawing? If it were me, I'd still be drawing. All right, I hope you're with me here. So, Emma, what was your answer to this one? S to R. Anybody else think the same kind of idea? So it could, because if I walk this way and I walk this way, it would be the same as walking like that. That would be the shortcut. It's not actually the same like trip. I wouldn't see the same flowers along my walk, but I would have the same outcome, and that's what vectors are talking about. Mason, you had something else. Can you tell me what you had? I want somebody to confirm or challenge that this is the same as ST plus TR. Is it? You can't confirm or challenge yourself, Mason, no? I see a few people nodding their heads. Emma, what do you think? Very nice. I also agree. Absolutely, and again, but it seems maybe counterintuitive that those two trips work out to the same, but the vector PQ is equivalent to the vector SR, so that would absolutely be valid. All three of those things would be equal to each other. Very good. Okay, and this is where we start getting into more interesting ideas that some people would try to argue SR is the only one. You take out the T and you get S to R, but actually, no, you could, it's also equal to PQ, because vectors is, in mathematics in particular, it's irrelevant from where the vector starts. That's typically not what we're talking about. Now, sometimes it is important where the vector starts, but that's a separate issue. So SQ plus QR would be SR. So SQ plus QR takes me just to SR, right? That vector there. And same as question A. ST plus TS. Zero vector. Okay, so again, those are some of the basics, I feel like. And then we get to question D, which is a little bit different. So how are we going to do this? And part of the reason is all three of those questions were set up tip to tail. So you could just walk the path and figure out where you ended up and just take the start of the path and then the end of the path and disregard everything in between. I hope you follow me. What if it doesn't work out that way? And vector addition, that's fine that it doesn't work out that way. It doesn't have to. So how am I going to do this? What I would say is, if you can walk the path and you can do it all in one step, fine. Don't force yourself. Don't rush. Sometimes we like to split this up into several questions. So SR plus RT, what's that going to give me? That part's easy. S to R, then R to T is the same as S, the vector ST. But then I'm adding that to itself. Those certainly are not tip to tail. Vector ST plus vector ST, is that 2 vector ST? Maybe, but we want something a little bit more interesting to be able to call that. What could you call that? Is it 0? They're in the same direction. ST plus TS would be 0. ST plus ST. SQ. Why is it SQ? But how do you know double? Like, well, and when I look at the diagram, there's a reason why those are in there, right? It's telling us that those are equal so that I know that this is ST here and ST here are actually the same length and everything, right? So if that was missing from the diagram, you might need more information to actually solve this. But very good. We could call this SQ plus QP. And then this one's set up, I guess, in the right way that I can just say this is equal to SP. PT minus ST. How can I think of this? How do we subtract vectors? We just did it. Add the opposite. What is negative ST? What's an equivalent vector to negative ST? Turn and talk to your partner and make a guess with them. See if you can figure it out. Just quickly. Okay, what do you think? TS. Anybody else think of TS? Are there others? Yeah, probably, but TS is probably the easiest one. Don't overcomplicate it. If you can make it simple, make it simple. And look at how that works out. Okay, try the next one on your own. So I hope you started with this. We don't have to do the step where we show that we're adding the negative. We can just add the actual negative vector because, you know, writing it twice is the same thing. So, but you can if you like. I'm talking about this step right here. I don't really need both of those written down, but I think you want to write one of them down. Probably, and this one's probably easier so that it's actually adding and it's an actual real vector. And that's going to, especially now, I mean, if you tried to just do this by visualizing, it's a lot more taxing. Okay, so then this works out to PR. And what's PR plus TP? Because again, this is a great example of a question that's not quite set up properly. So PR plus TP. Good. So do you know what the answer would be? PT. So what I'm saying is we walk from P to R. Here, I'm going to use this. Okay? And then I walk from T to P, which is here, from T to P. But that's as if I was walking from R to T, so it's the same. So where do I end up? My resultant is from P to T. Right? That's the idea. Very good. Okay. Another kind of question. This is just another kind of example that we do. Express A vector in terms of B vector and C vector. So we're going to have A vector equals some expression. If we're visual, if we've done a lot of this in physics, I know you haven't done exactly this in physics, but if you're just like vectors and you're visual and that kind of thing, you might just kind of be able to see it. I don't know. And if you can, by all means, go for it. What if you can't? I can give you a little tip. Go ahead and try it. See if you can come up with something. Okay, turn to talk to your partner and see what they came up with. Tell them what you came up with. Okay, let's take a look at this. I can imagine, now again, I talked to a couple people and they kind of, it was exactly as I suspected. Some people can kind of just see it, but if you can't, how might you solve this? Well, if you can come up with any expression relating to 3, you can rearrange. And what I notice is if I start here and walk, I get to a tail and I can walk again that way, which tells me that the B vector is equal to the A vector plus the C vector. If I do A plus C, tip to tail, that vector addition, I get B. So what do I do to rearrange this for A? I just move the C over and I have an expression for the A vector. But also, somebody else pointed out, if you start here and walk this way to get to A where you want to, the end of A to where you want to go, because I started in the right place, I have to do the negative of C. So it's like B plus negative C or B minus C would give you that. So kind of you can visualize it or you can write it out and rearrange. Either of those is fine. Okay, as I've said several times, there's three different ways that we're going to look at multiplying in terms of vectors. This is the super easy kind when we multiply a vector by a scalar. And you probably won't mix it up with the other kinds. It is intuitive. It is what you would expect, I think. And again, these little notes here, I don't even know if you really want to write them down, because it's really a formal way of saying what we imagine to be the case, what is you would think is obvious. When vector A is multiplied by scalar k, so what's a scalar? Wait a minute, what's a scalar? What is a scalar? Elf? Thank you, magnitude, no direction, so it's just a number. Just a number. When we deal with vectors, we can also deal with just numbers, but we call them scalars. And it's a big deal if we're talking about a vector or talking about a scalar. Things are very different. Multiplying a vector by a scalar is very different from multiplying two vectors, or multiplying two scalars for that matter. When a vector is multiplied by scalar k, the resultant vector is ka. That's just how we would show it, but you can usually simplify that. It has a magnitude of the absolute value of k times the magnitude of a. And it's the same direction as A if k is positive and the opposite if k is negative. That's all that's saying, k bigger than 0, k less than 0, right? Exactly what you'd expect. So if I take the A vector and multiply by -2, I'm going to flip the direction of the A vector. Okay? They're parallel. That's an important idea. And then this is just another definition before we move on, and actually we're going to show something as well. Vectors are collinear if they lie on a straight line when arranged tip to tail. Similar to parallel, but collinear usually means like they're actually in a line together because they're arranged like tip to tail kind of thing. So if A and B are non-zero vectors and A and B are parallel, then A and B are collinear, and A and B are scalar multiples of each other. What does that mean? That means, I was actually going to do some measuring here. Let's see. So I made B 3/4 of A, so B is equal to 3/4 of A, and there's your scalar multiplication. 3/4 times A gives me B, or A would be equal to 4/3 of B, right? So the scalar multiples of each other. You good with that? Couple more little details here. We're almost done. Tell me if I'm going too fast. So this is important. The resultant of scalar multiplication is a vector. When you multiply a vector by a scalar, you get a vector back. A vector that's twice as long, a vector that's half as long, a vector that's in the opposite direction. You think about what this means. Remember how we were talking about if two vectors are opposite, one is the negative of the other? So if I take one and multiply it by -1, I get its opposite. AB and negative AB, that's like -1 times AB, right? So, and again, we take that for granted, but what that's saying is those mathematical properties hold for multiplication of a vector by a scalar. And it doesn't have to. We saw this a little bit when we did derivatives, that sometimes our intuition, we believe that this would happen, but it doesn't. Okay, so that's the part that we take for granted. People would say, well, yeah, of course it does. No, not of course. But it turns out that it's true. Okay, and this is important. Distributive property holds. What is distributive property? Distributive property is this. Again, this wouldn't have to. But it turns out it does. And the associative property holds. What's the associative property? The associative property says order in which I do things. Does that matter? Addition is associative. A plus B plus C is the same as A plus C plus B or whatever. Multiplication is associative. So two scalars, k times n, and then multiply by the vector a, is the same as multiplying the vector a by n and then multiplying that by k. That's what we mean by associative. Boolean laws. Remind me, what do you mean by Boolean laws?
Like, in computer science, we do kind of the same thing, but we use it as in, like, trying to find why. So we do, like, associative law, commutative law, distributive law.
They certainly mean the same things. I'm curious about what activity exactly you're doing when you do that sort of thing.
Trying to find out, like, circuits, you know, like,
Yeah, okay, that's what I was wondering, if you meant like circuits. Yeah. Yeah, same kind of logic. Except we're not using circuits, but yes. Okay, one little example here. How can we simplify this? So I've got distributive property. And then because I have some of the same vectors, they're just like terms and I can add them together. When it's the same as your intuition and the same way you've always been doing it, it's easy to just not pay attention to it. If something comes up down the road that's different, then you're going to be like, ooh, I got to remember this one. Otherwise, I can just do it the way I've always done it, I suppose. And in this case, it's kind of the way you've always done it. Any questions?